All right, so we're looking at section 2.1, number 4. This is still just the introduction to derivatives. Again, we're just kind of looking again at what's the difference between these two formulas. So we want to be able to use both of these limit processes. Both of these are ways to find derivatives. However, this one is used if we want to find a general limit. And this one is used when we want to find a specific slope at one point. So both of these are really limit processes, but if it's just asking you to find just the derivative, if you want to just find the derivative, you should use this formula here. If you want to find the derivative at a specific point, like 5, 6, 10, 11, whatever, then you can use this alternative form. We talked earlier about the 3 methods for finding or estimating the rate of change, which is also known as the derivative. Numerically, does this give us an exact answer or an estimate? Estimate. So this is going to be an estimate. Analytically, what's that going to give us? Exact. And graphically, estimate. And that's why we want to use analytically as much as we can. And both of these are analytic methods. Both of those formulas are using algebra and calculus. All right, so just kind of reviewing. It says to find the derivative by the limit process, for example 1, then find the derivative at x equals c. So when they say these kind of directions to use that limit process, they want us to look at that delta x method. So we're going to go ahead and do that. So to do it, we're finding the general derivative first, the general limit. Actually, let me come up here. This really should be called the general derivative, not the general limit. General derivative. So we're going to be doing the limit as delta x approaches 0 of 2. Wherever we have an x, we replace the x with x plus delta x. We're going to square it and subtract 4. Now we have to do minus f of x. Notice how I changed this. Why am I changing this to plus 4 instead of minus 4? I'm distributing the what? The negative through, because it's minus this whole function. And then it's all over delta x. So now we have the limit as delta x approaches 0. I have to do 2 times. I want to multiply this all out. If I need to, I could use Pascal's triangle to figure out what the coefficients are. To the second power, I use this row right here. This is to the 0, this is to the first, this is to the second. So I know my coefficients go 1, and then I have to do x squared plus 2x delta x plus 1 delta x squared minus 4 minus 2x squared plus 4 all over delta x. Our whole goal is to plug in 0 for delta x. If I did it now, I'd get 0 over 0. So I have to keep working using algebra to simplify. If I have simplified correctly, then many of these terms should just cancel out and become 0. So looking for like terms, 2x squared minus 2x squared is 0. Negative 4 plus 4 is 0. Now we're just left with these 2 terms. What should I do with those 2 terms? All right, factor out a delta x. And I'm left with 4x plus 2 delta x all over delta x. I can cancel these. I really still have this limit. Now as soon as I plug in 0 for delta x, which I can do now I'm done with the limit. And I can say f prime of x is equal to 4x. That's my general derivative. But it's asking me to find the slope at c equals 3. So to do that, I'm going to find f prime of 3. That means in my derivative, I plug in 3 and I get 12. We're going to come down here to example 3 next. It says evaluate f of 3 and f of 3.01 for example 1. So I'm going to make a table of values. I'm going to plug in 3 and 3.01. I'm plugging those into that function from number 1. So when I do that, if I plug in 3, I don't need a calculator to plug in 3. 3 squared is 9 times 2 is 18 minus 4 is 14. When I plug in 3.01, I have to do 2 times 3.01 squared minus 4. And that gives me 14.1202. So I'm now using a numerical method to find my slope. This is just going to give me an approximation. So f prime of 3 can be approximated by doing y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's going to give me 0.1202 over 0.01. I multiply the bottom by 100 and the top by 100, and I'm going to get 12.02. And that's my approximation for the slope. It should be fairly close to what I got on example 1, and it is. All right, so now the directions say for number 2, use the alternative form of the derivative to find the derivative at x equals c. So now we're doing f prime of 2 equals, and now we're using this formula. That's the alternative form. I'm going to do the limit as x approaches 2 of f of x minus. Now, how am I going to know f of c? What do I do? Plug 2 back in. So if I plug in 2, 2 cubed plus 4. 8 plus 4 is 12. So I'm going to have to do minus 12 over x minus 2. I'm trying to plug in 2 for x. That's going to give me 8 plus 4. That's 12 minus 12. That's 0 over 0. I have to do more work. I want to divide this by x minus 2. But the problem is I can't factor like I normally do on these problems. How do I divide if I can't factor? Synthetic division. So what is it that would make this denominator equal 0? 2. So 2 is going to go in the box. I have to use the coefficient of x cubed. The coefficient of x squared is 0. Don't forget the 0. 2 and then negative 12. So anytime I can't factor, I'm going to use synthetic division. I bring this down, multiply, add, multiply, add, multiply, add. That's good because now I ended up with a 0. So that meant that these divided out evenly. And what I'm left with then is because I'm doing x cubed divided by x, this would represent x squared. So I have 1x squared plus 2x plus 6. I still have that limit because I haven't plugged in. Now I can plug in 2 squared plus 4 plus 6. What's that going to end up being? 4 plus 6 plus another 4 is 14. So f prime of 2 is 14.
How do you know what
Synthetic?
use like the derivative?
Oh, when to use which formula?
Yeah.
I could have used the alternative form on this first one, but it said to just use the limit process. When it says that limit process, it's usually meaning to use this general derivative formula. Yeah, you can use whichever one you want. In fact, on this one, it probably would have been easier to use this method, but since they told us to use that one, it was just for practice. Yeah.
So like on the equivalent test, you're going to say which one
No, I will always let you use whichever one you want. But if you're asked to just find the derivative and you're not given a specific point, you have to use this delta x method. All right. So now in example 4, it says to use your graphing calculator to find dy dx at x equals 2 for example 2. Well, this is just where we go to our calculator, go to y equals. I don't want to graph the derivative, so I'm going to turn that off. I'm just graphing my function, x cubed plus 2x. Oops. I'm going to do a zoom 6 to get a standard screen. Here's the way it looks. I'm now going to do second trace, calculate. I want to calculate dy dx. This really means the change in x over the change in y over the change in x. That means the same thing as slope. D really almost stands for delta. It's like delta y over delta x, change in y over change in x. So I go down to number 6. I put in the number 2, and it tells me that dy dx is 14.000001. And does that support the fact that the answer is 14? So you would want to call this 14. This is what the calculator says, but the actual answer is 14 because remember the calculator gives us an approximation. Okay, does that kind of make it clearer just seeing both of those side by side? All right, very good. Our quiz over this is not until our next block day, so a week from today. We'll be doing some other things, adding on to these limit processes, and then we'll take that quiz then.